Good morning, all. My name is Murali Krishna Gumma. I am coming from ICRISAT. I'm a remote sensing specialist and leading remote sensing GIS group at ICRISAT. As you all know, ICRISAT is one of CG center among 15 CG centers, which is non-profitable organizations. And we work on mainly, ICRISAT is mainly working on dryland areas, Africa, South Asia, and Southeast Asia. And our unit mainly we are supporting unit. We are supporting to the multidisciplinary teams, and we produce various products which are crop type, crop including irrigation source, land use changes, specifically specific crop wise how much area it is over the period it is changing, and length of growing period, cropping intensities, and abiotic stresses, mainly drought, submergence, and heat stress. These three stresses we are monitoring. And these are the products we are generating from imagery, and we are integrating with some secondary information and secondary data. We are analyzing for other products like climate change analysis we are doing, and land degradation, and prioritization of watersheds, and natural resource management. And this is mainly supported to the different disciplines. This is the background. Coming to this background, this is the outline of my presentation. I will show some of our recent work, irrigated versus rainfed cropland areas in South Asia and Africa. And second product is crop type mapping using Google Earth Engine. Of course, Google Earth Engine, we have some problems, issues with machine learning algorithms. So with semi-automated techniques also we are using for more appropriate maps. And finally, flood and drought using Google Earth Engine. And some of the issues, what are the issues we are facing in Google Earth Engine and traditional methods. And this is the, we use Landsat 30 meters data for map irrigated areas and total cropland extent. And mainly three data sets we have prepared out of Landsat time series data. Crop extent, irrigated versus rainfed, and cropping intensities, three products. But the crop type still we are working on that, but we did not get an accurate map. Yeah, this is the composite we are using season-wise data sets we have prepared, and we combined all together into the one stack, and a lot of ground data. Actually, we have collected the most of the ground data by our staff. We are traveling and going visiting some locations. We are collecting some information, geographical coordinates, crop calendar, crop intensities, whether it is single crop, double crop, triple crop area, and cropping pattern over the year, over the crop years, and previous years also we are considering. Because the main problem is we are not able to cover entire India at a time, but we are doing it in 2 years. That's the reason 2013 and 14 we have collected nearly 2,000 samples across India and Bangladesh also. And finally, irrigation techniques also, watering method, water application method, how many times they irrigate. And this is all data. In few points we are gathering all this information. This is as a training data, and we are generating some ideal spectra signatures as well with this information. But apart from this, we are gathering additional information, which is only crop type and only physical observation we are gathering from while driving the car, we are capturing that information. Here you can see the most of the green light color points, all these points, mainly where we visited, and we have collected a lot of information from the farmers and extension officers also. And where we are not able to visit the dark points, we are gathering from high resolution images, Google Earth images. And all these, wherever we have collected detailed information, we captured for some photographs as well. Here we are collecting as much as information. Previous years also we are gathering detailed information for these locations. And you can see the most of the where we are not able to visit those points, we are collecting from high resolution images. And this is the by using random forest classifier, we have mapped irrigated versus rainfed cropland areas in entire South Asia. But the major problem is some of rainfed areas also it is mixing with rainfed areas, irrigated areas. That's the reason right now we have presented only crop extent map, which is just published right now. And the ground data and all these algorithms are available in this LPDAC already. And now we are improving with the additional ground information and secondary information, statistical information. We are improving our classification, irrigated versus rain-fed crop extents. And similar way we have done for Africa as well, which is already published, and algorithms are available in NPDAC, and all ground information also available there. And now we are trying for small study areas, specific crop type mapping. For that, what we have data, that data is not enough. That's the reason we have collected specific districts, few districts intensively. We have a lot of ground information we have collected. With that information, we are doing crop classification. We have run here by using this random forest classifier. We got only 67.6% of accuracy, but still we are refining that one. This is by using Google Earth Engine. If we run by semi-automated techniques, suppose 50-60% of process, all initial process we run by Google Earth Engine. Then after that, a spectral matching technique we used. In that case, we got very higher accuracy. If you see here, for Jhansi, one of the study district, here the small fragmented area, different cropping pattern, you can see that clearly here, but which was not captured previously by machine learning algorithm. Yeah, here it is. Even field boundaries also not captured properly. And here it is a semi-automated technique. We got 83% accuracy with limited ground data. But wherever we used more ground data in machine learning, Google Earth Engine, we got very less accuracy. And similar way, the same methodology we applied for Kharif season as well. But Kharif season, due to the cloud cover, we are not able to extract exact classification. But now we are combining with the Sentinel-1 and Sentinel-2. We are refining the classification methods. In similar way, flood mapping, especially in some of the study regions, we are working temporal flood areas to recommend flood-based farming systems. You see here very accurately, this is all done by Google Earth Engine. And similar way, long-term drought pattern, how it is varying in Myanmar. These are the case studies. And major issues, we are not able to standardize algorithms for specifically crop type mapping, and different length of grain. The major issue is, South Asia and Africa, mainly small holding farmers, and also field by field, different crops are there, which is very difficult to capture. We are not able to capture that one, and also we have limited ground information. We need more and more. Where we are collecting the ground data along the roads, we are not able to go to the interiors, which is very important for training data. And intercropping pattern, which is especially in dryland areas, the 70 to 80% of area, it is intercropping pattern. For example, cotton mixed with one line cotton and one line it is pigeon pea or some other crops, which is very difficult to differentiate in cropping pattern. And variability in the field. Within the field also there is a little bit variability is there. Some area it is high vegetation, some area low vegetation. That is also becoming a problem. And these are the conclusions. We mapped out the crop extent, irrigated versus rain-fed areas for South Asia and Sub-Saharan Africa using Google Earth Engine. Now, semi-automated technique with the Google Earth Engine and spectral matching technique, we are able to classify very exactly which we are going to use, those products we are going to use for crop modeling, yield assessment, and for other interventions. Yeah, we have contributed several publications on Google Earth Engine. Thank you.
Okay, thank you. We start from here. Brazil is the 5th largest emitter of greenhouse gas emissions, and it's basically land use, the big chunk of them. So for us, it's very, very important to kind of understand what happened with the land use. So normally, for many years, we were very good to actually know one simple transition, which is not actually a land use. It's just like there's forest, there's no forest anymore with deforestation. So the challenge that we put to this big group of organizations here is to find out what are the other transitions, how this is happening over the time in Brazil. So this starts back in 2015. It's a group that involves NGOs, universities, and startups in technology, and the idea is to develop a large time series of land use maps in Brazil, and then allow us to understand the land use change, and then the emissions and so on. So it's based on Landsat, processing pixel by pixel, a lot of machine learning and cloud-based processing. When starting 2015, there was not too much exercise on large scale to do that, so we kind of are creating our own Brazilian way of doing things. Learn a lot of things in the process. And so today we are in the collection 4. So there was 6 collections. This is like collection 4 now, which works with 20 classes. And what we have is this is turned into a platform. By the way, it's like the global accuracy now is about 85%. There is all the information on the accuracies for each of the classes, for each of the years, and you can get the whole picture. Obviously, it's not like the same accuracy for all the classes and all the years, but that's the general. And so it's a platform where you can get the maps for every single year, and you can navigate and understand this by the whole country or for a specific biome for each one of the 5,000 municipalities or the states, or each one of the watersheds, and etc. And it's all pre-calculated, so it's kind of a help to anyone to navigate on the history of the land use in Brazil in the last 35 years. So you can go to places like, this is the middle of the Amazon, this is 85, and this would be like 2017. And then you kind of, so you can navigate a space and time. And also there is a tool that allows for people to compare any pair of years and understand what are the changes that happened there. And do this in as much detail as possible. So if I take an example of one municipality in the Amazon, that is 85, this is 2017, and then if I can compare the 2 years, then I can get where are the changes. The red stuff is obviously loss of natural environment, but I want to know more specifically what specific transition interests me. For example, if I'm buying soybean from the Amazon and I don't want to buy soybean from deforestation, so I just want to know this specific transition. So you go there, you choose the transition you want to see, and then it goes back to the map, and you have exactly that transition, where they are located, and then you can plot all the properties of the country, and then you can see which specific property have that specific transition for that specific period that you are interested in, things like that. And also the platform allows for analysis, like, for example, you can run a buffer analysis on every single infrastructure on transportation and energy in Brazil. So it's kind of a very practical, directly related to use cases for the different people that need this information in Brazil. There is secondary products that is being produced, like, for example, this is you can derivate information on deforestation, like grass deforestation, net deforestation, deforestation of only from secondary forests, or deforestation of primary forests, or just natural vegetation. There is all those kinds of different things that you can imagine after you have this time series put there. Or analysis like this one, where we separate artificial water streams from natural water streams and see that, for example, the surface of natural water streams in the Amazon is actually declining very fast. So yeah, so this initiative is running in Brazil for the last 4 years. Now it's there is different setups of groups that we call like the MapBiomass network, where local groups also in other countries are developing the same idea and strategy in Indonesia and most of these countries in South America. Cool. How in time? 2.5 something? Okay, 4 minutes, okay. So this is in a very simple way, what's the general strategy of the project. So depending on the theme that we are mapping, we use like mosaics of Landsat, annually mosaics, or we use the entire collection of the image and process all of them. So for example, if you're talking about mangroves, we use the entire collection because it varies a lot, the water. So you need to have like more observations in the years. But the interesting part is that we don't, we do the classification first with the map separate. So we map like the forest, the water, the agriculture, etc., all separate. And then, so to get the best map of each one of those classes, and then afterwards, we just stack all of them together, have a series of prevalence rules to actually make the whole map after it's done. We did several tests of doing it in different ways, and we find out that when you have like up to 5 or 6 classes, the algorithms work well in terms of differentiating, but when you get to 20 classes, it's really confusing. And so we find out, in our case, it's better to actually have some kind of a separation, and you get the best map of each class, and then you find out a way to kind of put a puzzle together in the end. So after doing the classification, we do a lot of temporal and spatial filters. So we use a lot of temporal information to reclassify some of the classes. For example, if you want to separate natural forests from forest plantations, it's very difficult spectrally speaking. So we just say like if it's forest, 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 no forest, 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 no forest, 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 that's a forest plantation, for example. So then you can reclassify the whole thing. Cool. So yeah, that's the basic approach. We do, as we were talking about a lot about this, the sampling. Obviously, we do a lot of sampling and training data for the classification, but we also do a separate big data just for the accuracy assessment. So the basic approach there's many things we do for training data, but this is like the most like the basic one that everyone is using on the different themes that we are working. So we divide the country in those 558 tiles, and also using the biomes as reference, which are the core parts on the map. And so we collect hundreds of polygons inside of those tiles. So this is actually the analyst chasing out the classes that we are mapping on those tiles, and then creating those polygons that represents those classes. And they, as they collect those polygons, they actually classify that over all the period of time that we have on the map. So they try to get to design the polygons on areas that were stable as that class during the whole period of the analysis. So you have 34 years this tile as a forest, and you know that this is a forest in all the process. So you get a kind of so you guarantee that this is like a good sample for that for all the period. We estimate that we have about like over 5 million pixels if you sum up all this the styles that have been used, and we keep adding information on this on this data set of training data on every collection. So we keep adding information. And one interesting thing that we find out is that every time we have field visit, workshops, and even feedback from the users, when they find out something is wrong, oh, this map is not correctly in this specific place, we go there and then we collect more samples and add to the database and just keep going on that. That's for the accuracy assessment. Last year we kind of created a totally new data set with 100,000 points. In this case, like we make a sample 100 stratified distribution in the country of this 100,000 points. So in this case, obviously the analyst is not choosing. We just give those points, and they have to pass for 3 analysts to be included. Yeah, and they use Landsat, and also if there is available high resolution imagery, they can also use that And again, they do the classification of that point, or the identify what is that label for all the 34 years of the collection. So then we have this data set now that can allow us to kind of assess the accuracy of the map also over the time, which changed a lot. That's interesting. Like there is a lot of change on the accuracy depending on the year that you're analyzing because of the different qualities of the image and so on. I would just pass this. Yeah. So the data that is available today is like the land use maps, and also the land use change maps are available all the time series at the pixel level. There is this 10 million label samples. I say 10 million here because it's kind of two data sets that we're using different periods of the collection, so they're all there. And we have 100, the 100K samples analyzed for the 34 years. So the way it's available today is as assets on Google Earth Engine. So the annual land use and time series is open. It's there, just like you just go and check. And as for the label samples, as we are still working out on the best way to present the data, we are doing case by case. People ask to use, and we just go and kind of curate for them how to use the data, what's in there, etc. It's not well documented as it should be yet. So, but we will arrange a way to do this quickly. So we want this to be released as soon as possible. Anyone can have access to that because it's a hell of work to do this damn labeling. So we don't want people to be using their time to do that. And the scripts, it's all on GitHub. I just took this information because I found it interesting in terms of how these people are using that. So last year we had like we tracked 93 papers published in 2009 using this data, those data sets, on peer review documentation, right? Which was a big growth in relation to 2018. And our impression is that actually the idea of using time series in large scale and using cloud computing, et cetera, is actually gained momentum last year. So it's not because you had or not the information available, it's just that people are now getting the tools and experience to actually use that, right? And then just in terms of the access on the internet, 68,000 users last year, and 5,000 of them, they have actually registered to access the database and exchange views and etc. So I think it's a big number for this kind of a very troublesome bunch of data. Anyway, yeah. So I'll stop here.
All right, trying again. Hi, my name is Chris Brown. I am the ML lead for Google Earth Engine. Real quick, I want to thank NASA, Radiant Earth, Ahmed for giving me an opportunity to speak today. So just click, cool. Right, so originally I wasn't going to talk about this, but being here, and first I want to say it's also been really exciting to see Earth Engine finding its way into your research in all of your projects. I can see the little logo sometimes in the bottom left-hand corner or something like that. But every time I hear about somebody who's building a new database, or we have to build this thing to be able to do our analysis. And I think I heard that enough times over the last day that I was like, okay, I should probably just talk a little bit about what Earth Engine is in case you don't know what it is. Right, so we'll go through this real quick. Google Earth Engine, what is it? A lot of you probably already know this, but if you're not familiar, it is our cloud platform for easy petabyte scale analysis of satellite imagery. So what does that mean? Okay, I mean, you can say that, but what is this tool? So it's actually two pieces that are integrated very tightly. It's a data catalog and a computation platform. So again, that's very vague. What does that mean? Well, we're talking from something like Python, from JavaScript, an API, and a user interface called a code editor. You can access this computation platform and the data catalog without the need for packages, imports, Docker containers, building your own database, any of that. Again, kind of zooming out or zooming in a little bit even closer, we're talking, so if I'm in this code editor, this UI that I'm not even going to bother showing because this is just kind of really just a brief introduction. If you're not familiar, we can do things like Landsat8.filterDate, pick 2 dates, reduce mean and reduce median or something like that. And literally in seconds, you can hit run and you're seeing pyramided. So at any zoom level, something like a median composite. Or if you're doing something globally, you can run a long running task and get the same thing. So it's pretty incredible, right? This is real time built on Google infrastructure. Obviously that wouldn't be useful if you didn't have a data catalog to work from, right? So being Google, our interest is to organize the world's data, make it universally accessible and useful. So things like Landsat, the entire catalog from 8 back to 1, Sentinel-2, Sentinel-1, Sentinel-5P, MODIS, any of the public imagery that you can really think of is in our data catalog and is just as easily accessible and usable kind of in that really brief kind of 3-line example that I mentioned. Tabular data as well. So things like country boundaries, ecoregions, any of these sort of tabular data, and even joining tabular data and raster data. This isn't something we have to go into NumPy and start sampling things. It's really sample regions, polygon, raster, that simple. And again, this is not designed just to be easy, it's designed to be scalable. It's what we use internally. Google teams like Google Maps use Earth Engine internally to operationalize things like our building detection, our street sign detection, things we've been doing for years. Yeah, and of course, it's only so useful if you can bring your own data. So if you have things like TIFFs, CSVs, shaped files, TF records, anything like that, you can ingest that into Earth Engine and use them in the same way that you can use any of the other data. And if it's not already obvious, this tool is completely free. So for NGOs and researchers, this is a really great way to actually get computational scale without having to go pay for it or build another system built on Docker containers and AWS and all these other things. Or no problem with AWS though. But it's a common pattern, right? A lot of people talk about doing that specific thing. Or GCS, people do that too. But okay. But that's right, that's something a lot of you already know. What I think is really interesting is to talk a little bit about Earth Engine and sort of modern machine learning. So didn't really mention it, but Earth Engine for a while has had some classical machine learning built in. So we're talking things about random forest, tree-based statistical classifiers, things like that. Things that you can sort of run in real time, right? So to train, for example, a decision tree is very rapid, right? And then applying that can also pretty much happen in the scope of me interactively moving around a map. Things change a little bit sometimes if I want to work with a neural net, specifically a large one. So recently in the past year, we have been upping our integration with TensorFlow specifically, so that now you can start to apply machine learning models built with TensorFlow at scale in Earth Engine. Again, we want to work from small, something like regional, something local to something global, and the experience should be the same. So just a brief example, there's a lot of different frameworks going around. Somebody was talking about really interesting sort of unstructured data for doing graph neural networks. For ocean currents, for example, a lot of common use cases are star CNN-like use cases. If you really want to stride a convolution, really you mean striding a fully convolutional neural network. Object detection, super common patterns, some for high res, some for low res imagery. Recently, we launched a tool called EE Model that allows you to, just like any other Earth Engine, reduce, filter, select, any of these really simple operations that let you scale geospatial computations, you can now do with neural networks. And it should be just as easy, and it just folds into your script like anything else. So what is this powered by? Cloud AI Platform. So GCS, we have things like AI platform training and prediction. So what you can end up doing is taking a model that you've built in TensorFlow, trained it in something like AI Platform. You're not spending your own resources. You're not having to have your own cluster to do this. And then with a button click in GCS, that model is now an AI platform. And with the command from AI Platform Predictor, you are now using that model you trained. We are automatically scaling it. We are moving border artifacts, for an example, if this is something like a fully convolutional neural net. And we are automatically handling all of the projections, right? Even if you have data in 30 different projections, we get that into one projection and it just happens automatically. Really, the whole goal is to make this easy. If you have imagery from 3 different sources or something like that that are in multiple projections, that is all just handled for you. And of course, you can control all of these things because it's not just meant to be a, an evaluation platform. This is something that's meant to be for research production. So of course, we can now take even a step higher and move into other free tools like Google Colab, where you can actually start to develop models in free IPython sort of Jupyter Notebook environments, which is really cool. Once you start to pair all these things together, you're in one environment, it's all very seamless, and you can start to deploy models at scale using Earth Engine and TensorFlow. And we have docs for all this too. So once you want to start going big, you can start to do things like using an Earth Engine batch task. If you're not familiar with Earth Engine, I kind of quickly alluded to that. This is something like a long running task. So if I really want to run inference at scale, for an example, or I need a ton of training data, I can export all of this to GCS and now use something like a cluster on AI platform to train it. So I'm going to kind of hurry a little bit because I'm now talking longer about the thing that was just supposed to be an afterthought. Anyway, so it's super cool. We have docs if you want to learn more. But okay, this is also interesting. So originally I was going to talk a little bit about dynamic world. So you've heard this, Steve spoke about this yesterday. We have a whole lot of machine learning verticals at Google. Specifically though, we're going to talk about this one because this is super applicable to what we are talking about today with a lot of public data. So just real quick, dynamic world. I copied this slide from Steve. The only difference is I put Google at the top. This is our collaboration with WRI and National Geographic to build a 10-meter Sentinel-2 based land cover map, starting with a map for 2019, and then start to turn this into something that we can build a change detector off of. Again, our mission is certainly about making data universally accessible and useful. So if we can start to make land cover one of these universally and accessible, useful products like satellite imagery, these derived products, that's really our goal. So I'm just going to go quickly through this. So kind of what we were looking at here was, do we really want to use UNet? Do we really want to use something like a deep lab, right? Originally, our goal was to work with static imagery, right? There's a lot of benefits for scaling if you're working with static image analysis. Also, depending on your taxonomy, if you're working with a taxonomic kind of classification like we are, you can get away with something a lot smaller if you're working with medium to low resolution data. You don't have to start to go up with something like UNet that has 4 million parameters. I know I'm really jumping the gun here, but you guys are all machine learning people, so you get it. Right, so there's actually a whole lot of benefits once you can start to reduce the weights. You can start to fit the whole thing on commodity GPUs, which is great if you want to open source something, and there's no requirement for an up path, so it's a sort of cyclic. If you can reduce the receptive field, if you don't need so many weights for a model, things start to get a whole lot better. So we actually wanted to analyze, what does that mean? Can we empirically evaluate what is sort of the minimum viable, or where's the saturation point for these types of models, right? Because we don't want to screw around with UNet. This is something built for a specific task. We've all been using it, but let's actually do an architecture search for something a little bit better. We set up one such thing, some details about what we did there. And in short, generally good news. The hypothesis was sort of verified that receptive fields are super small. Of course, as we learned in another project, working with something like a 3x3 neighborhood specifically doesn't work when you're doing things like wetland detection with static image analysis, because you need to be able to detect features that aren't necessarily in that 90 by 90 meter neighborhood. But really quickly, just to kind of allude to what all these crazy random looking points are, the fact is that they appear to have very little structure. And for example, what we're really plotting is certain hyperparameters versus the % average recall. And this was our sort of our control, something that's pretty obvious and known to have a strong effect, right? So this is batch per replica in this case, and we see an actual saturation, which is absolutely expected. But there wasn't the same behavior when we were dealing with model parameter count. And it's a little more complicated, but in this case, it's been simplified to just be multiplier times the actual number of stages in sort of this block-like, exception-like neural network. Anyway, so your models can be small, that's the point. And there wasn't a strong correlation between this sort of parameter count and model performance, and we wound up with something that was equivalent to anything we were getting with 4 million parameters, with 100K parameters, just using best practices and actually doing this architecture search. I know I'm totally out of time, but this is super cool. So I do really want to get this bit out there. So we were beating this over the head in our session yesterday, but any of you who are actually machine learning practitioners, something really easily you can do, so like we're doing in Dynamic World, is using our known annotation quality as a prior. So it takes a lot of work to make sure labels are really, really high quality and all are perfect. Sometimes you have to do that depending on the machine learning algorithm you're using. If you're using something probabilistic though, you can start to use that as a prior. So what we in fact do is we treat our workforce labels as being less confident than our expert labels. And actually, when we train the model this way, instead of treating everything with the same confidence, we actually do a little bit better. Last thing I'll say, Steve also mentioned yesterday that in Dynamic World, we don't require our annotators to annotate the full patch. We want to cover more of this land cover class manifold, not necessarily smaller parts in a really accurate way. So by doing this, we, again, large wide open area, but we don't require full coverage, right? Because we're working with a fully convolutional neural net. Obviously, what do? Do we treat this empty class as just a don't know kind of thing? You don't actually have to do that. This is somewhat common knowledge, but I think it's also worth talking about here. You actually want to stop back propagation at the points where you don't know what the label is instead of treating it as an unlabeled class. And you can do this by masking. And this is just sort of a brief 3-line proof as to why this works and why you should really be doing that, because you don't want to be incentivizing the model to make predictions. And in fact, when you don't know what the label is, you want it to actually try to make a correct prediction there. Those are really kind of broad way to talk about it. Anyway, but we can start to bring all these things together, right? And it starts to be really cool. We can take this platform Earth Engine where we just say from AI platform predictor, predict image, and start to take our dynamic world models and put them right on top of there. I didn't talk about how we're doing things like splitting these up kind of per ecoregion biome and how our training procedure is actually working. But you can really get a sense of how easily we get to scale this thing, right? Because A, we have a taxonomy that works for static image analysis. We're performing static image analysis, and we're running it using e.model and Earth Engine. So we can start to do things like live inference, and then much easier, just scale this globally with actually a button click. So that's really cool. That's all. Thanks, guys.
No, it's okay. I was going to do the animation at a later date. No, now you messed it up worse. Hold on. Okay, this is where we're at. Thank you, Hamed. Hi, everyone. I'm Brookie Guzder-Williams. I'm the Director of Data Science at WRI. I've also been doing a fellowship for Radiant Earth. I'm going to be continuing this year doing it. It's been great, and they're the ones who funded this research, so thank you. So we're talking about surface water detection, Q animation with Sentinel-1. So if you're interested in where water is and has been on the planet, there's a great product out there, the Global Surface Water from European Union's Joint Research Commission. What is it? It's a Landsat-based product. They have data from 1984 to 2018. It was released in 2 big chunks, initially up through 2015, and then recently they updated it through 2018. It includes a monthly water history, and everything I'm talking about today is analogous to their monthly water history. Also a recurrence and annual classification. So they have a nice interactive website, an accompanying Nature article, and an Earth Engine asset. So if you're interested in water, this is a great place to start. So why are we doing anything else? Well, our main motivation is we want something that's near real time. We don't want to have to wait a couple years for the next update. Specifically, if you're interested in ephemeral water sources and how things are changing, maybe for malaria risk maps, et cetera, you want a near real time, at least monthly updates. Along the way, we're going to move over to Sentinel, get a little bit higher spatial resolution, clean up some Landsat artifacts, and hopefully improve the accuracy a little bit. So if you've never looked at water in radar data, it's really easy to see. I'm guessing all of you guys can find the water in this picture. So a good place to start is just simply by trying to do a simple thresholding model. Clearly, there's a clear water signal in this, so each of these columns is a slightly different set of thresholding parameters. But some of the difficulties here is finding consistent parameters that are going to work across scenes. And then you also have this speckle that kind of gets introduced from the SAR data. You could probably fix this in a very straightforward way. So you could start doing thresholds based on kind of dynamic global properties of the scenes and areas. You could smooth out the input by taking like a stack of images and taking the mean or some other method, but we're not going to do any of that. We're going to throw it into a neural network and see what happens. So let's start talking about that. So for the pilot that I'm discussing today, we're actually using JRC's data as ground truth. So we're taking the 30 meter and we're downsampling or upsampling to 20 meter and just saying this is ground truth. Now that said, We are then, which is what I'm starting to work on right now, going to take the data that Steve mentioned yesterday and was just briefly mentioned in Chris's talk as well, from this Dynamic World project with Nat Geo, Google, and WRI. But that said, we took from these areas in Southern Africa, we broke it up into 384 by 384 tiles that contain some amount of water from 0.5% to 90%. We did a train validation split based on these 1 by 1 degree tiles. So you can kind of, I don't know which is which here, but it's like a tile of train, test, and validation. We then did this other thing, which I just mentioned because I think it's a little less standard, but I'm doing this more in my projects. We randomly selected these data points. So you end up with overlapping tiles. And what I did then is took a 0.01 by 0.01 degree grid and labeled all of my tiles. And anything that overlaps within that grid, we treated as data augmentation. So when we went through our training loop, so you can kind of see a few instances here, like this and this would probably be completely different tiles, right? But these three here would all be treated as the same point. So just like I'm also going to flip and rotate this, I flip, rotate, and then randomly select one of these. So it's like kind of these little shifts. And so I just treat it like data augmentation. For our network architecture, we started with DeepLab v3+, because we thought we were fancy and started modifying it. We eventually dropped the ASPP block, which at that point, it's kind of a stretch to even say it's a modified DeepLab v3+. And then we just started, and this is the network we actually, everything you're gonna see results from today, this is what we used. We also, some of the other differences we made was reducing, like we used the exception backbone and kind of reduced, we only have one block in this entry flow. And it's worth mentioning, I then took this same model and started applying it to another project I'm working on, and then began stripping that down more. There's this bottleneck piece where they were going through it 16 times, and I reduced that down to 2. And then there's these convolutions on this output, and I dropped those. And so I've really simplified the model at this point and was getting pretty much the same results. And this echoes exactly what Chris was just kind of beating home, that you can really simplify these models a lot of times, depending on what you're doing, and still get good results. But for the specific results today, this is the model I was using. And these are our training curves, some of the prettiest training curves I've ever had in a project, which is completely reflected in the fact that it's such an easy problem. If you go back to looking at that VDVH slide I showed you, it's easy to see water. And so I have these beautiful training curves, and they're even more beautiful when you realize the orange is the validation set. But here's going into an actual accuracy assessment. You see I've listed precision recall and F2 here, and we're scoring around 90%. Broke this up into monthly data sets. I'm breaking it up per month. This dip here you're seeing in 1 and a little bit in 4 are because there was less data. Like we actually only had 1 data point, and I wasn't very careful. And it wasn't until I made this slide that I was like, what's going on in January? And then I realized I only had one example in January. So that is what happened there. This is same thing, breaking it up over per biome. And generally, we did well across biomes. There's this tropical and subtropical moist broadband forest over on the far right, which again was due to lack of data. This red one, the flooded grasslands and savannas, is a little more interesting. That's where we were actually not performing as well. And it's not surprising that the flooded grasslands, I think both I think this is probably due to us having a harder time and also due to error in the JRC data. But this is like, so this is an area we can do further model improvement. And hopefully when we move over to using true ground truth with the dynamic world data set, that's a place where we're going to clear up some of that. And here are some examples. And they, you know, you can, the far right column is the JRC data, and the one in from that is our prediction. And then you have VV and VH. I don't know why I did that in right to left. But so you can see it matches up really well. This second row here, something happened in the JRC data. There was some, you know, clear, something didn't match up correctly, and you can see we fixed that up. Here's a set of examples where the red in the JRC data is there no data. These kind of fixed lines are some of the Landsat artifacts I was talking about. And this speckle, I'm not sure what was going in, but they had some no data value and that goes away. But in general, we're really matching up quite well. And that's it, that's where we're at. So what are the next steps? So we will take this and either it trains fast enough, we'll probably retrain from scratch and fine tune what we've done here using the dynamic world data set and see how that works. And then we're gonna extend the data Africa-wide, produce maps from 2015 through the present and operationalize it for monthly updates. And once that's all working well, and we haven't hit any problems, we'll try to extend this globally. And as mentioned before, this work was funded by Radiant Earth, and you know, it's been great working with those guys, and thank you so much.
Thank you. Good morning, everybody. Thank you very much. As Hamed mentioned, I'm from George Mason University. I recently moved there about 16 months ago, and I used to be in South Africa at the CSIR. So half of the work will be work I started over there at CSIR, finished up here, and the rest will be some new work. Okay. Just a click. Okay. So we have all these satellites, and I heard the other day, we are swimming in satellites and drowning in data. And we therefore have this Earth observation data tsunami. And people are trying to make sense of this. Users cannot consume the data fast enough. And so the operators cannot interpret all of these imagery using conventional methods. So therefore we need machine learning to interpret and classify all this data. So other people are being employed to visually interpret the imagery to generate the training data. And there's a certain irony in this, but I like it. And I actually feel sorry for people that spend a lot of time generating all this training data. I'm glad for them. It generates work, but I've tried it. It's really, really hard. Now you can convince yourself that you're having fun at 11 at night while you have a whiskey, creating this training data, but it's really rough. So personally, I'm a bit more lazy, so I try to generate automatic training data from ancillary data sets, generate large amounts of training data. And I'm just going to show two use cases that have some relevance to this workshop. The first one is really creating woody vegetation structural metrics from synthetic aperture radar and training it with airborne LiDAR data. And we started this work in Kruger National Park in South Africa. The white areas are LiDAR data collected by the Carnegie Airborne Observatory during 3 missions to South Africa. And we demonstrated that we can use this airborne LiDAR data to train random forest models to predict woody vegetation cover and biomass in savannas using synthetic aperture radar. Many people work on this problem, but they focus on high biomass, tropical rainforest. We work at the lower end where it's a little bit more difficult, lower biomass. So the question then is, can one scale this up to country level scales. So here's more than 120 LiDAR data sets. And there's an old saying, go big or go home. So we said, we're going to take this problem on. We're going to process all these diverse LiDAR data sets and see if we can build a system that can map at a national scale. So how do you generate training data from LiDAR? This is just a Google Earth backdrop. You can see the trees. There's a canopy height model. The whiter it is, the higher it is, the vegetation. At 1 meter resolution, you can see some power lines that we just threshold out of there. And from there, you can calculate percentage vegetation cover, tree cover at 25 meter ALOS pulsar scale. And that becomes your training data, all of this LiDAR. So the work I'm going to show focuses on Namibia, my favorite adopted country at the moment. If you ever get the opportunity, go and visit Namibia. Louisa is from Namibia. And 50% of the rangeland areas are considered to be bush encroached. That's 26 million hectares. And the loss in meat production annually is about 100 million euros. So there's a big incentive to map and monitor woody vegetation cover and debushing activities which remove these trees at great expense. So the objective was to develop a machine learning system that can map and monitor fractional woody cover at 50 meter resolution at national scales using synthetic aperture radar data, training and validation from very diverse airborne LiDAR. And the red areas are the airborne LiDAR data. The backdrop here is a map of woody vegetation density. And this is all they have to work with at this point in time. And you've got millions of euros in aid focusing on this problem, yet your geospatial information to drive the policy and activities are not there. So we hoped we can do better. So we have a very large training data sets, 244,000 hectares of airborne LiDAR. So we believe that that stage of machine learning approach was potentially justifiable. We further investigated the representativeness of the training data here, just looking at elevation versus mean annual precipitation for the study area in blue versus the LiDAR data in orange. And you could judge that there's a fairly good coverage, except for the very arid areas where there's no trees. And the products look pretty good. This is just east of the Tosha Pan, very encroached areas. If you drive along that road, that's what it looks like. And people actually remove areas, commercial farmers, cattle farmers pay folks to produce charcoal and remove those trees. So these activities can now be monitored, and areas in red are areas that are where the trees are removed. In blue is where they grow back. And you can see there's a national preoccupation with debushing. So, but now getting into the machine learning side of things, we had to add precipitation as an ancillary variable because we had overestimates in woody cover due to slopes and rough surfaces in the very arid areas. So when we added, so that you had that overestimation over there of fractional woody cover at low precipitation. When we added precipitation and corrected that, you got an R-square of 0.74. But what you got are these anomalies in your data. And at further investigation, I found that somewhere in there, the random forest made a very hard decision boundary that created these discontinuities that follows a 387 millimeter mean annual precipitation. And I attributed that to the limited training data below that threshold, and that essentially the random forest made that decision to do that and produce that artifact. We had to follow a different approach, therefore, to counter this. And it comes back to that concept of how do you then use your biophysical model, in this case, just fitting a line at the upper envelope of this fractional woody cover according to the LIDAR versus mean annual precipitation, and combine that with a product that did not use precipitation initially, okay? So lessons learned. So the geographic distribution of your training data can cause a lot of bias and lead to regional anomalies. Now, these artifacts may not be as obvious as you see here, and I believe there's other products out there that have these artifacts hidden in them. R-square is not really a very reliable metric of model predictions, and you can have very different models with the same R-square. You have to interrogate your model outputs. The distribution of your training data along the range of the values have a very large influence on your machine learning predictions. Class imbalance, you're very familiar with that. And therefore, because the model fits to the majority of the data, the distribution of your data is very important. And by subsampling your data, changing the distribution of the data, you can improve the accuracy in certain ranges of your predicted variable. More training data is not always better. The distribution of the training data makes a very large difference. We applied the same approach to the whole of South Africa to produce a biomass output. Then the next use case, this is about quantifying training data representativeness for scaling up convolutional neural networks to large geographic areas. This pretty much tests the first rule of geography, saying everything is related to everything else, but closer things are more related than things that are further apart. Therefore, training data will be less representative of test areas that are further away. And the objective here, and then I'm going to rush and wrap up, is to explore the relationship between the representativeness of training data measured in feature space and the accuracy of convolutional neural network-based classifications with increasing geographic distance between training data and deployment area. So we're essentially testing this hypothesis, whether Euclidean distance increase with geographic distance, and that representativeness of your training data will reduce. So it's essentially testing this translocation generalization that people referred to yesterday. This will help us understand training data requirements to enable CNN applications over large areas and kind of temper our expectation of the relationship between training data and your expected accuracy. We focus on the Chesapeake Bay catchment, for which there's a lot of training data, and we're essentially doing this. We have, at this moment, 6 counties around big cities where we create training data. Then we apply the model and the training data developed here to the next one, and further away. So with that, I'll have to stop there. I don't have the final results of this. This is my PhD student's work, which I don't want to scoop, and it's still in progress. So this is what I'm testing, trying to understand how do we generate training data that's representative to lead to reliable models. Thank you.
All right, hey everyone. So I'm going to be talking about our work on human-in-the-loop framework. Thanks. Human-in-the-loop framework for fast lane cover mapping. So first of all, this is in a collaboration with many people. Special thanks to the Microsoft AI for Earth team, who I've closely worked with on all of this. So we're trying to do a deep learning approach to lane cover mapping. Specifically, we take high resolution input images and train a convolutional neural network to label each pixel in the input imagery as belonging to one of several different lane cover classes. And our goal is to create high resolution lane cover maps that fit with local stakeholder needs. And this is the important part here. We want to know how lane cover models trained in one area can be quickly adapted to work in different areas under different constraints. So for example, if you have a model that's trained in Maryland and it's performing quite well, how can you then adapt it to different places in New York where local stakeholders have maybe the need of testing on different sets of classes, or they have different constraints on the precision and recall metrics that they need. So some potential approaches here are to completely revisit your modeling assumptions. You might want to try different modeling approaches, retrain the model with different hyperparameters, use different data, all these sorts of things. But I claim that this isn't a scalable way to solve this problem. Local stakeholders aren't going to be able to do this. If you're partnering with a conservation agency, they don't have unlimited interns or grad students or data scientists to throw at this problem every time they need land cover data, highly specialized land cover data for a new application. So the second way is to fine-tune existing models with new data. So we can simply query labelers for new data and then use that new data to adapt these models accordingly. And I'm saying this is scalable because local stakeholders are going to be able to do this if we provide them with the right tools. What do I mean by this? We've done this by implementing an interactive web application that we can directly deliver to local stakeholders and customize more easily to their individual needs. So kind of very dangerously, I'm going to try to do a live demo of this. Let's see how this goes. So what you're looking at here is Sentinel imagery from Ho Chi Minh City in Vietnam. This is the platform that we have running now. It's running on Azure VM. And what it lets you do is run inference with a deep learning model that's doing this link over classification task, like I said. So just looking at this, you can see that this is not making the correct predictions, mainly because it's not trained properly. But what this tool allows you to do is provide training data points and retrain on the fly. So I'm going to say this area here is classified as water, not built up surfaces. Maybe select the field class and give a couple of training points here. Select the tree canopy class and maybe, I'm just toggling the opacity of the layers, by the way. Maybe this stuff is tree canopy. And then finally, a built up surface that's being classified as water here. So now that I've done this, I can press retrain and the final layer of the model is retrained with the data that I just provided and the new predictions from the model are shown on the screen. So if I keep running inference now, I can see these new predictions and find that they're matching up with the imagery much better. So just a final thing, once someone has iterated on this process for a while and are happy with kind of the model that they're observing, they can then run the model over a larger area by clicking download, right? So now this model that I've just fine-tuned is being run over this much larger area, and you can see the results here. And then they can go down and download this as a GeoTIFF, or maybe get class statistics over this area. So back to the slides. What I just did from a research standpoint is acted as an active learning query method within this tool. So I first clicked around on the map and observed the model's predictions, found based just on looking at the imagery and the predictions where the model's making mistakes, labeled places that I thought would be helpful for the model to see in a retraining process and retrained the model. So this is kind of very similar to an active learning method, but instead of using uncertainty as a criterion for picking the points that we want humans to label, the humans themselves are picking those points. So we tested this, how well this is able to work in both an offline study where we compared existing active learning methods with fine-tuning methods for adapting a model to a new area. And I say offline study because we're simulating human labelers with known ground truth data. And then we picked the best kind of method out of this set that we tested and tested that against actual humans using this tool in a crowdsourced study. So the best method was actually just random selection of points. This is an example of one of the areas that we're looking at. It's about 85 kilometers squared. And we found that the users are actually performing better than the random selection of points when they're given this tool to work with. So what this graph shows is that over a 15-minute time window, on average, when users are using this tool, their time would be spent more efficiently than if they were just being presented pixels to label one by one. And further, we find that there actually exist super users that are actually very good at doing this, several standard deviations above the average user, and that those users are indeed detectable. So we're quite comfortable saying that people are going to be able to use this tool effectively to kind of customize these land cover models. Just going a little bit more into detail about what the users are actually doing, we find they're not behaving randomly at all. We look at the distribution of the points that they're clicking compared to random selection of points in terms of the model's uncertainty or the model's class entropy. This is the graph on the left. And we find that they're selecting points in the mid-entropy ranges, which is kind of not common in the random, but also not what model entropy-based active learning query method would do either. The distribution of points in comparison to distance to the nearest edge, we find users are selecting points that are always close to some edge, whereas in just the random distribution, you have points that are kind of far away from everything. So we know that they're not behaving randomly, but we don't know exactly what the users are doing to actually get this gain in performance. So just to summarize this, we've proposed modeling human-in-the-loop methods in an active learning framework. We compared different methods or different query methods and fine-tuning methods in this offline study, then performed an online study comparing humans to the random query methods. We find users are outperforming random selection, and we say that local stakeholders can now use this interface and methodology to tune existing models to maybe new areas that they care about. And just briefly about other work that we do, we have this ICLR paper called Label Super Resolution that where we propose a method for training models using both low resolution data and high resolution data. So that's pretty interesting. We use this technique in a CVPR paper where we train models that we use for 1 meter level land cover mapping across the whole continental United States. If you want to find out more about this work, you can go to this website, aka.ms/land cover mapping. We have all the code available. We have all the papers, a data set, and all that. So thank you.
All right, thank you. My name is Fishgold, and I'm a software engineer at Azavea. And I'm going to just be going over like an overview of some of the projects we're working on. So first, Azavea is a geospatial software company located in Philadelphia. We have about 60 people, and we've been doing more and more work on doing deep learning on satellite and aerial imagery. And we're a B corporation, and that means that we're somewhere in between a for-profit corporation and a nonprofit. So when we want to make profit, but we also have I guess a social mission. And our mission is to advance the state of the art in geospatial technology and apply it for civic, social, and environmental impact. So as part of our mission, we try to create a lot of tools and then make them as open as possible for other people to use. So I'm going to be going over 3 tools that are all kind of interconnected. And they take you from unlabeled imagery all the way to trained models that you could actually deploy in an application. So I'm going to go over these in more detail, but there's Raster Foundry, which does imagery management, and that leads into Groundwork, which is a labeling tool. And then Raster Vision is an open source framework for actually training models on this type of data. And Stack is the glue that ties these all together. Okay, so first, I'm just briefly going to talk about Raster Foundry. So this is an app that lets you upload imagery to the cloud, and then it will create ZXY tile servers that you could use in various apps, as part of Slipy Maps. And you can also do various queries and visualizations on that imagery. So once you have some imagery in the system, you can export it to Stack, and then you might want to actually label it. So this is what Groundwork does. It's a labeling tool that is specifically for geospatial data. So you might wonder, why would we build our own labeling tool? Because there are labeling tools out there, things like Labelbox that people have mentioned, but these don't work very well for the geospatial use case. And there's also things like QGIS, but QGIS isn't really meant for, it's not really designed for doing like labeling things for machine learning. All right, so we built our own tool, and these are some of the nice properties of it. So first, it can natively handle geospatial file formats and open standards, things like GeoJSON and Stack. And one of the problems it handles is that it can handle like the really large images that we're used to dealing with in GIS. And it handles that by breaking them into small parallelizable tasks. And then each task can be worked on and labeled by different labelers. And then, since it's our own tool, we have the ability to add other GIS-specific features, like the ability to add map overlays, and some of these things you can see over here on the right. So, we can switch between different base maps. We have like transparency sliders. You can see labels that are in adjacent tasks that other people have labeled and things like that. And, in the future, we want to add support for things like time series of imagery, which comes up a lot. So there's a little tour of the different computer vision tasks that you can handle in this labeling tool. So the first one is chip classification. So in chip classification, we divide the image up into a grid, and then we want to classify each cell in that grid. So this highlighted area is just the current task that the labeler is looking at. So this is just a very small piece of the larger scene. And then you can just click the class that you want. And there's also some nice keyboard shortcuts. And then when you're done, you can confirm it and move on to the next task. There's also support for semantic segmentation. So this is pixel-wise labeling. And we also have support for object detection / instance segmentation. And this is where you want to actually localize individual instances of some object, something like buildings or buses. And so if you have a team of labelers, it's nice to be able to look at the activity of the different labelers from a bird's eye view. So this view just shows you the activity over a specific scene over here. You can look at how many tasks have been completed over time. And there's also metrics on different labelers. Sorry. And then the last thing about this is that we can export the data to a Stack catalog. And from there, you can use whatever tool you want with it. And there's going to be hopefully a free version available in March. So if you're interested in this, please get in touch with me and I can try to connect you with the right people. All right, so now that you have some labeled imagery, you need to actually train a model. And there's lots of nice open source libraries for doing deep learning out there, but they're not, most of them aren't well designed for handling geospatial data. And as some other people have mentioned already today, there's a lot of kind of repetitive grunt work that everyone has to do over and over again every time you work on a new project. So we decided to try to abstract out some of this functionality that's common across these projects into an open source framework, and it's called raster vision. So raster vision, the way it works is you write a configuration, and the configuration points at some inputs, things like images, labels, and AOIs. So AOIs are areas that you want to actually train the model on. And you can also specify other things like the type of computer vision task, the type of backend you want to use, like PyTorch, and other hyperparameters. And then it will run this whole workflow in the cloud. And it handles all the idiosyncrasies of geospatial data. So it does analysis, will produce some metrics on the data set. It'll create training chips. So, neural networks can't take in 10,000 by 10,000 images, so we have to chop it up into smaller pieces. So it does that, it does the coordinate transforms. It trains the model, makes predictions over scenes, produces evaluation metrics, and then bundles things together into a package that has the model and some metadata so that it can then be run or deployed somewhere. And raster vision supports these different computer vision tasks. And like I said, it's a framework, so it's meant to be really flexible. You can kind of fill in the blanks with application specific things, like you can add new tasks, new label sources, new backends, but the main backend that we're supporting is PyTorch these days. And so raster vision was released. We had like our first alpha release about 1.5 years ago, and so we've been using it a lot, and there's also some people in the community using it. And based on this feedback, we're in the process right now of more or less rewriting it to make it a lot more, like the code base simpler and also more modular, so it's easier to customize. And hopefully we'll have like a 1.0 release in the middle of the year. So now I'm just going to briefly go over some applications we've done using these tools. So this was for a water utility company. So they flew drones around some water tanks, and they had like a tank management system, and they want to like automatically prioritize tanks for maintenance. So this was to find rust spots. So each cell is like orange if it's predicted to have rust. This is for like a gas pipeline company, and you really don't want people digging next to a pipe because there could be a very costly explosion. So they fly airplanes over the pipeline like, on a regular basis, and they want to just find heavy machinery and stuff nearby. And this is a project for the International Development Bank, and this is where we were trying to just find buildings in Latin America. So yeah, I think that's it. So thanks for listening, and talk to me if you want to be able to like use any of these tools.